In this video, we present our method for grasp-oriented non-prehensile manipulation. The goal is to autonomously reconfigure objects into graspable states before executing a grasp. In real-world manipulation, objects are often placed in unfavorable configurations. Even when feasible grasps exist, a direct grasp may fail due to poor alignment or unstable poses. Therefore, the robot must first manipulate the object before executing a grasp. Recent approaches formulate manipulation as a goal-conditioned control problem, where the robot is trained to reach a predefined target-object pose. However, such target poses are often difficult to obtain in practice, as they typically require object-specific annotations or external planners. In addition, many objects admit multiple graspable configurations, and selecting a single target pose may not reflect how the robot should manipulate the object. Instead of predicting a specific target pose, we learn a graspability field over object configurations. The graspability field measures how suitable the current object state is for successful grasp execution. This scalar signal provides dense supervision for reinforcement learning and indicates when manipulation should transition to grasping. In addition, the policy predicts the distance to the graspable region and an executable grasp pose, which together guide both the manipulation process and the final grasp execution. During training, we use a teacher-student framework. The student policy observes robot states and partial point clouds from cameras. Inputs are encoded into robot and object tokens and processed by a cross-attention policy with learned queries. The student predicts the manipulation action, the distance to the graspable region, and an executable grasp pose. For supervision, the teacher policy has privileged observations, including the full point cloud. A pre-trained grasp pose model uses the full point cloud to generate reference poses. The teacher action then supervises the student action during training, enabling manipulation from partial observations. In simulation, the policy successfully reconfigures objects into graspable states across diverse object geometries. The robot learns to push, slide, and reorient objects until the predicted graspability becomes high enough to trigger grasping. We further evaluate the policy on a real Franca robot. The learned manipulation behaviors transfer from simulation to the real world, allowing the robot to autonomously reconfigure objects. When the predicted graspability becomes sufficiently high, the system automatically stops manipulation and executes a grasp without requiring external planners. We further evaluate the predicted graspability distance. Graspable configurations consistently produce smaller distances than non-graspable ones. A simple threshold can clearly separate the two groups, enabling the robot to automatically stop manipulation and execute the grasp. In summary, our method reformulates non-prehensile manipulation as optimizing a graspability objective. This enables a unified policy that autonomously prepares objects for grasping and transitions to grasp execution.